Sorry?
Less mathematical.
Yes,
Okay.
it is less mathematical than we have historically taught this content.
Wow. I know computer science required a ton of math stuff, but still, that is quite a lot of math, even for a class like this.
Yep.
Computers don't do math.
That is also true.
It breaks down into math. Everything we do, every algorithm we write breaks down into math. So you can understand it in a roundabout way or in a direct way through math. All right, we should get started. I first wanted to double down on the question I started last class with, which was, do we have any questions on the study plan? Are there any clarification questions, expectation related questions? Have you thought about any questions related to how should I prepare for the exam? What should I be studying? How should I be spending my time? Any clarifications?
Like if I were to do the substitution method, and as long as I can get it, like what we were talking about yesterday, to that point, like, is that fine? Like, do I have to write the summation?
I would, if you can, write the summation, and if you can, solve the summation. But every step that you can take will be significantly more, at least partial credit in the problem. And I am designing these to not be the most intense questions we've seen in this class. Like our general philosophy when I have a lot of questions to design and not a ton of time for the outcome of the exam.
So if we don't solve the summation, we're still not gonna get 100%.
Depends on the problem. So if the problem will state either relate type bounds or relate a summation, or the problem will state what the expected end result is. And the expected end result will be based on how complicated that is and whether we've seen it before in class.
Okay.
All right, let's do 1, then 2, and there are a couple of questions in Zoom as well that I need to address.
Yeah, so I know like writing down something like the master method. That's even how I want to word it. I need to say is as like the master method and maybe write some minor things you have to go about substitution. Are there any general formulas or pieces of knowledge that recommend that we write in advance on?
For the master method or for the substitution method?
Well, no, I just think those kind of examples of what I already kind of
Yeah,
but
like what the master method is. I would absolutely have all of the rules of the master method on there for sure. I would write down any sequence that we've seen so far in class and just kind of how we've solved those that isn't intuitive to you. Basically anything that isn't intuitive to you, that you can't just pull from the knowledge of your mind as you study, something that says this would be good to remember, or I'm not sure I would remember this on the exam. That's what I would put on the study guide. There's a lot of prior material. If I'm writing questions, I'm going to be asking generic questions that may rely on some of the knowledge that we've talked about in class. Either people are going to remember that, or rather than try to memorize it, throw it on your sheet. That's just kind of it's a place to dump all material that you don't want to memorize that you think may be relevant. Because I hate all of it. But that's the general approach I would take. And that's going to vary student to student based on where you are, what you understand, what you feel like your strengths and weaknesses are with regards to the material we've covered.
Have a whole exam that you'd be willing to put into practice exam.
I want to give you one from another class. I have never made one for this class. So I'm designing it from scratch. There is no old exam, but I could give you potentially something that is along the lines of the design of my kinds of exams. It's a good question. I'll try to get to that. If you're looking for that later today and you can't see something like that, maybe I can share something, send me a reminder. I'm gonna get to the couple that are on Zoom and then I'll come back to rest in class. General, just how should we prepare for the exam? I think Colin's question did a pretty good job of addressing that, just trying to figure out what your strengths and weaknesses are, what you feel like you would otherwise be memorizing, don't spend your time memorizing anything, throw it on the sheet. Anything that is a generic, how do you do this process? That's what you should either know or have some steps for. If I see a problem that's related to an indicator random variable, here are the steps that I would go through to recognize what is the query variable. How do I represent it as an indicator random variable? How do I solve for an expected value given an indicator random variable? Something like that, with maybe an example of that. You can absolutely throw examples from class or examples from the book or anything. I'm not going to look at or collect your note sheet. So there is nothing that is good to put on there, bad to put on there. You're not cheating by putting something on there. I literally do not care what is on that sheet, whatever is useful to you. Preparing for the AVL portion. So yeah, the kinds of questions I would ask, there's not much I can do with an AVL tree. So you can expect that there is a question along the lines of, here is a binary search tree, perform an insertion or a deletion by hand, doing the associated rotations that are required to adhere to AVL, and then relate the tree. There's not too much else I can do with that, aside from some generic questions of how do you handle, what complexities are associated with, how does AVL assure that we have that logarithmic time insertion and deletion. Those kinds of questions you should also be aware of and know or have access to on your study sheet. So to kind of higher level questions that prod at the understanding of it. But with regards to the actual implementation, there will be no code. It will only be performing insertions, deletions, and rotations and identifying when and how to do the aspects of the pieces of that. That's the way. Daniel, did you have a question?
Oh, yeah,
No, I'll come back to you.
the question I had was, here on the study guide, one of the questions is, what simplifying assumptions do we make when analyzing in algorithms? Asymptotic complexity relating to constants and lower order terms.
Yeah.
Isn't that just, I don't know, when I read this, for some reason, the wording was confusing me. Rereading it now, isn't it just like, why do we get rid of constants and why do
Yeah.
we get rid of?
Yeah,
like,
being able to
overhead?
identify, maybe I would ask you a question like, what are the simplifying assumptions?
Mhm.
List them and then justify why they're
Why, yeah.
not relevant to asymptotic complexity. What is it about a constant? If we subtract a constant, if we multiply by a constant, why is it that does not change the asymptotic complexity? When we subtract off a lower order term, why does that not change the asymptotic complexity? Collins and
Yeah, very quick one, now that homework one grades have been posted, will there be like an answer sheet? I kind of look back and see where we messed up.
So yeah, the book questions are findable if you are diligent. A relatively easy to think of search query will give you the first or second result that is just all of the answers from the book. That's not particularly useful or recommended while you are working through the assignment, but I think that the graders are already working through and going to start working through the next assignment that's been submitted, or is going to be submitted next week, I guess. So they have exams to grade this weekend. They're going to have the next assignment to grade as soon as those are done. I don't anticipate they immediately have time for coming up with that. I would rely on the book answers that are out there, and then I'd be happy to handle anything in office hours that is, how does my answer differ from this? Is this the same? Is this different? Can we go over what the expectation was and how that differed from what was there? I anticipate, especially since this is both of their first time grading algorithms, that there may be some concerns that you have about grading or questions that you have about grading that need answers. And I very much want to provide you with those answers, potentially changing grades where that is needed. So just recognize that everyone is doing this for the first time. Don't bury your frustrations. Come talk to me about it, and I can at least get you the outcome, if not change things to make it more fair. I would eventually like to make an answer sheet for all of these, but I don't know if I'm going to have that prepared for this quarter, given how busy everybody is.
I just want to go back to that question of the simplifying assumptions. Are we able to briefly go over that real fast? Just because I feel like I know some of them. I'm wondering if there's some I'm forgetting about.
Yeah, so it boils down to the ratio of the functions over time. That's the way that I like to intuitively attach myself to that. If you're looking at, we have two functions, f of n and g of n, at n as it varies from 1 up to infinity. What is the ratio of f of n divided by g of n, or f of n to g of n at each of those places? If we have a constant that is something like a factor of 2, then f of n divided by g of n will always be 2 or 1/2, whichever is just larger. But it doesn't matter where on that x-axis you are in terms of, I guess, the n-axis in this case, but how large n is, the ratio of their differences does not change. And that tells us that the size or the scope of the problem is not what's responsible for the differences in their running time. Whereas if they're in a different order, then that ratio is changing. It's getting larger and larger and larger, or smaller and smaller and smaller, tending toward infinity or tending toward 0, depending again on which is larger over time. And the limit as n reaches infinity is that there is no bound to that ratio. So the size of the problem is very responsible for the differences in their complexity. And that is why we say they're in different asymptotic orders. So that could be any multiplicative constant, but it could also be an additive constant. The value that that additive constant has on the ratio tends towards 0 as n gets very large. So if I add 5 operations from f of n to get g of n, as f of n takes 10 steps to solve, g of n takes 1.5 times the time. But as f of n takes 1,000,000 steps to solve, the ratio between 1,000,000 and 1,000,005 is so small that it's irrelevant. The difficulty of the problem is based on the size of the problem, not the differences in the algorithms. So we're really looking for when is there a difference between these algorithms as the problem size increases. And that only occurs if we're in a different asymptotic order, not because of constants, not because of lower order terms, because even those go to 0 as we get larger and larger. So the difference between n and n squared, when n is 10, is a factor of 10. When n is 100, it's a factor of 100. When n is 1,000,000, it's a factor of 1,000,000. It grows based on the size of n. The ratio of difference, again, tends toward infinity and continues to increase and increase and increase. So we know that they are very different algorithms for that reason. Does that make sense to people? Any further clarifications I can make from that, or follow-ups from anyone? That's how I handle a question like that on an exam. Other questions before we dive into some randomized algorithm practice? I guess there's one more announcement I can make, and that is how I typically design exams. I don't like to make the exam out of the number of points that it is worth. I like to make them out of more than that for 2 reasons. One, I try to build in a reasonable curve to the exam so that I don't have to curve it after the fact. I still usually have to curve it after the fact, but expect there to be more than 100 points on the exam that is worth 100 points. So you can look at the exam as I hand it to you, and you can see that there are 105, 110, 120 points, depending on how difficult I think the exam is going to be. And that way I'm not doing things like scaling everyone's grade up by the same amount. I don't like to do that. I like to place credit where credit is earned, make you earn the credit, but scale it based on your level of knowledge. So the more you know, the more you can relate, the more your score will be curved by the fact that there are more points available. So that's one thing that you can expect. How many questions will be on the test? That's a good question. It depends on the associated level of difficulty. So if there are more challenging questions, there are fewer. If there are less challenging questions, there are more. I expect a diligent, studied student to probably take about 50 minutes for the hour-long exam. That's the target that I am designing for. So if you find yourself needing to do a lot of looking up or remembering or working through something that you didn't diligently study, you probably have about 10 minutes of total time on the exam for that process. So it is worth your time to be prepared, to have things on your study sheet, to be referenced where possible. What else can I answer? Yeah.
So for 2B, it says be able to calculate both the depth and breadth of the recursion tree. So is that just like finding base case for the depth? Like you have to know like how many.
Yeah, how many recursive calls does it take to get to the deepest base case? As well as when you analyze kind of the number of leaves that are the base cases, how many of those are there? Because that creates an upper bound to the size of the recursion tree. If you have that depth times the breadth, that gives you a very good upper bound. You can relate that in terms of a big O. Because it's not really a rectangle, it's more like a triangle, but you can use the geometric shape of that recursion tree as an estimate of complexity of the problem. And it tells you kind of that level order analysis, as well as you need to know how many times to apply that level order. You can figure out the total complexity of the first level, the second level, the third level, knowing how many levels there are, tells you how many problems there are going to be in both the axes of envisioning this kind of like a triangle. Looks like we've exhausted the questions. Any last minute questions? Okay, let's dive into a first practice problem. This question is worded a little strangely. It says the expected value of a maximum of 2 thrown dice, 6-sided dice. This means that when you throw those 2 dice, the result of that throw is whatever the value is on the larger of the 2 dice. So if I throw 2 dice and get a 4 and a 2, the result of that roll is a 4. Think of it as if you play D&D, rolling with advantage. What is the value of rolling with advantage when you throw 2 dice? You're going to take the higher of the 2 value as the output of a throw.
Sense? It's expected value, I really got a practical.
As you get started, this is the exact scope and complexity that I would like to throw on the exam. The reason I like this question, as soon as I saw it, I was like, yes, this is exactly the size and scope of a problem that I think is solvable in an exam.
Two thrown to 6 dice. Expected value, nice. Wow, okay. Wow.
How we doing? We think we have an answer? We stuck? So let's start with a little bit of intuition, because I like intuition, at least to ground yourself in these kinds of problems. How many different possible outcomes are there rolling 2d6? 36 possibilities. So we should be able to break down those 36 possibilities into their associated values. How many ways are there to roll 2 dice and have a maximum of 1?
One way.
So if we have the 2 dice be a 1 and a 1, that is the only way to have the maximum of a 1. There's one way to do it. How about 2?
2, 1, 1, 2.
And 2, and 2, 2. So I'm gonna start the left die as small as possible. And keep the right die as large as possible for as long as I can. And that's how I'm gonna be ordering this. For 3, how many are there? We would have 1 and 3. I'm gonna keep this as large as possible. This is 2. This is small as possible. There has to be a 3 between these. So this can be a 2, 3, a 3, 3, a 3, 2, and a 3, 1. 5 possible ways. Anyone see a 6th that I missed?
No.
There is no 6th. What's the pattern we are seeing emerge?
It's about like 2 combinations are being added for every number we're going up.
This is odd numbers. What happens if we take 1 plus 3 plus 5 plus 7 plus 9 plus 11? What does that sum to?
So 36, yeah.
Which is the total number of combinations that we expected there to be. Interesting part of this, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and 6 squared. As you add the odd numbers in sequence,
Oh.
you get the perfect squares. Intuitively drawing this out, it kind of makes sense. If you have a square of size n by n, what does it take to get a square that is n plus 1 by n plus 1? If you extend this, you're going to get, this is 1 times n, this is 1 times n, and this is 1. So you're adding 2n plus 1 to get the next value of an n plus 1 by n plus 1, and that maps to exactly what we're doing. So when we want to go from 3 to 4, this 7 breaks down into 3 plus 1. Prior value, the prior size of that square. So you end up with 2 new, I see it geometrically, and I think that helps it make sense as to why this evolves the way that it does. Also, you can see this inductively by looking at, there's always this middle equal value. And really all we're doing from these values to get here is we're changing the high value. So this 2 becomes a 3, this 2 becomes a 3, and now we need to break this into 2 additional new pieces that slot in there. And this stays and becomes that and that. So we just need to add the 2 that are on the other side of the equal part. So that's how I break this down inductively and visually to see that. So when we see this, we can start to rewrite this as an expression based on the weights of how likely this is, plus or times the value that we get. So the value of the highest roll being 1, we should have a 1 times the likelihood of getting that, which is 1 out of 36. To add to that, we have the weight here, 3 copies of getting 2 out of 36. There's 3 out of 36 chance to get a weight of 2. Flip that. Plus, to get a weight of 3, the probability of getting that is 5 out of 36. And as we do this, what answer do we get?
Find out we don't.
Someone calculate that real quick.
I'm already on.
I can give you an intuitive way if you don't have a calculator with you or don't want to go through all of this to try to figure that out. You could by just changing everything to be out of 36 and straight adding. I'll give you an intuitive way to at least get a ballpark.
Now I can. Look, I got a ton of practice recording. Oh, wait.
Seems like we have 4.47. That track with someone who's in class.
Getting close anyway. 1 sec.
Good.
Yeah, that's about right.
All right. So let's give you the reasoning or how we could get there. If there are 36 possibilities, where are we in this sequence when we have reached halfway into it? So when we're adding this, where are we when we reach 18? 1 plus 3 is 4, plus 5 is 9, plus 7 is 16, plus 9 is 25. So it's going to be somewhere in between here and here. This is after we reach 1, 2, 3, 4, and before we reach 5. So I can already tell it's going to be 4 point something. Why? That is where the median piece of this is with regards to its weight. So very fast ballpark. Doesn't get us a ton of the decimal. You can see based on how far we are into this, between the 16 and 25, the 18 is reasonably close to the 16. But the end result is, that would make me want to guess, it's a little bit less than 4.5. But again, that's a very ballpark way of doing it. It's reasonably easy to get an exact answer here, but if you don't have time or access to resources, or just want some mental math way of approximating something like this, that's how I do it.
Hey, are you okay with us having a simple calculator at the exam?
I can't assume that everyone has access to or can bring a calculator. So if I think that a problem requires a calculator, the way that I'll word it on the exam is leave your answer in the form of an expression. If you would like to spend the time to evaluate that for your own value, that's fine, but I will not require exact answers where that will require something like this. If you left the answer like this, just as an expression, great. Don't spend the time to derive the exact 4.47 or even 161 over 36. It's probably not worth it. As long as you can derive the expression, I will recognize that you can evaluate that expression, but you've shown the work of, I know how to solve this problem. Questions on rolling with advantage? All right, let me at least reveal the next one so you can get started, but it's in this section where I wanted to do this work. Oh, I'll just finish this real quick. All right, question out of the book. I'm gonna have to zoom in on this because it's a little bit larger. Where we go? Should have broken this up a little bit more. All right. So one issue we have in computer science is the limits of an integer. We can get around the limits of an integer by doing something like making a big integer class representing integers as strings and doing string-wise math on large numbers to create the string that is the larger number. If we didn't want to do this and instead wanted to use an integer, but we wanted to be able to represent numbers that are larger than the maximum value of an integer, one way we could do this is we could trade off the maximum value of an integer for a precise value of the result that we are calculating. So if we wanted to do some kind of counting procedure, potentially getting above an integer, we're going to use Morris's probabilistic counting algorithm, which says that we have a counter, and instead of counting every single time, we're going to probabilistically increment the counter. And as we proceed, we're going to have less and less of a chance of incrementing that counter. But the questions that we could ask about this is, what is the expected value of how many times we called probabilistic increments versus the actual value that the counter is showing us? So it might be showing us 10,000, but we actually called it 12,000 times. But because of the associated underlying probability, we could come up with an expected value and a variance for how many times we actually called the increment given the value that is shown. That gives us a normal distribution around that value. You're most likely to hit the exact value that it probabilistically states, but based on the number of times of the calls to increment, we get a different deviation from that. So we lose the precision of the counter, but before that counter rolls over to the negative value from hitting integer max value, we could represent numbers that are a lot larger. This is way too large to throw in an exam. I would not do this to you. That's why I started with the other one. But this gets a sense of your intuition. If you can look at a problem like this and solve it, you're well prepared for the exam. So let's spend some time thinking about this. Recommendation for you. I see a lot of people just kind of looking at it and looking at the question is to model this as an indicator random variable. Where success is we increment the counter. Failure is we don't increment the counter. Doesn't really matter if we're assigning that to the concept of a success or a failure. It's just a way of representing a binary problem. Then you can find a way to take the expected value.
Just trying to truly understand this
Yeah,
is all, and trying to understand what it means. And to be honest, I was not paying attention to some of the stuff that's sorry. Okay. Okay. Alright, so the expected value was. Okay. I have not practiced enough.
and this is probably more complicated than I would throw at the exam.
Well,
I'm doing this one to build some intuition.
on a bit of a screen.
Given the amount of time we have, something like 5 minutes to talk about this. Anyone want to talk through a process? If you've managed to make some progress, you don't have to have a solution, but how did you approach the process?
Well. Right. Also, we're trying to find the expected value of 2 minutes. 9.2 wrong. 6 days, so we found it, so will we start with that for this, to get through this problem? I'm not sure if I'm being honest, but.
Yeah, it's going to depend on this expression. That gives us kind of the probability that we are incrementing or not incrementing. The problem doesn't state what the probability is going to be. It just gives us a test bed to allow us to have any value between 0 and 1 as our success, as our failure. So the expected value is going to be based on those variables. You can ground yourself by setting something like let's assume that we probabilistically increment 50% of the time. So the probability of an increment is 50%. The probability of failing to increment is also 50%. If that were to happen, equal likelihood. What happens if we call the increment once? What is the expected value of the counter? We either incremented it, probability 0.5, or we failed to. So it's either going to be 1 or 0, equally likely. That expected value should be 0.5. What happens if we call it twice?
Okay.
Yeah. Yeah.
So then it would be.
Yeah, this ends up just being a binomial. How many successes do we have? But it's kind of an inverse in that we're looking at, we see the result of the number of successes as the counter, which is what we're looking at. We're trying to go the other way to find out how many times was this operation called when we see the number of successes. But we also know the underlying probabilities of that. So that allows us to at least say what number of trials would have been responsible for the number of successes that we've seen. What are the error bars on that?
Oh, now I.
But this will be normally distributed because it is a binomial. And what we know about those is they have means and standard deviations. So part A is really just asking, why is the mean guaranteed to be where it is?
Should these.
So let's go through, I have to zoom out in order to reveal the next thing. Here's our indicator random variable. Just this first part is part A. This is A, starting from here is B. This is less relevant to us. So modeling this with an indicator random variable.
Oh, I think you get it now.
So we model this with an indicator random variable. We see that the counter has this value with that probability. The numerator and denominator are the same here. They cancel and kind of leave us with, if we do this n times, the expected value of each of these is 1. At least it's based on that. So you end up with n copies of our successes. So it's at least proportional to that n. The variance calculations, don't want to worry about too much, but the expected value of that, we just see that we can move that expected value inwards. And we see that we do this n times, n counters. And we look at, we're just taking the expected value of the indicator random variable, which turns out to be 1. And we do that n times, giving us the expected value of n.
Okay.
This is probably, it's definitely too much work for an exam question. But again, I like to throw these kinds of practice problems. I like to throw typically one that maps more directly to the exam and one that is meant to be intriguing, related to what we are studying in computer science, and something that is worth studying on the side to build that, why is this the case? So,
Ow.
I will have office hours for the next couple of hours. Again, I don't usually or don't state that I have them on Thursday, but that's only in a worst case, especially for an exam, I want to have them. So feel free to come ask me questions, ask for some practice problems, anything else that comes up. I'm happy to help to whatever extent I can. I will see you tomorrow for the exam.